Bismillahirrahmanirrahim. Assalamualaikum students. Welcome to Electronics. I am Madam Rosminazwin Abdurrahim. Okay, as usual, let's have a look on this hadith. Abdullah ibn Mas'ud reported, the Prophet ﷺ said, there is no envy but in two cases. A man whom Allah has given wealth and he spends it rightly, and a man whom Allah has given wisdom and he judges and teaches with it. Source Sahih al-Bukhari. Okay, this hadith is kind of important to us because in our life, where we have social media around us, we tend to be envy. We tend to get jealous when we look at Instagram following the public figure, the Insta famous. Okay, we tend to envy their branded things, the way their lifestyle, what did they do. Okay, but it's not actually permissible in Islam. In Islam, there are only two things that we can envy. The first one is to those who Allah has given them wealth. Okay, they are rich and they spend it rightly. Okay, obviously in a good way. Okay, to give sadaqah, to help people. And another one is the man whom Allah has given wisdom and he use it wisely. Okay, he judges and teaches with it. Okay, so these are the two people that you should be envy of. Okay, then make sure you have a correct idol, role model that you can follow, because obviously when we have this envy feeling, we try to imitate to be like them, right? Okay, so hopefully we can be one of those, either a man whom Allah has given wealth and spends it rightly, or a man that Allah has given wisdom and we use it for a good purpose, inshallah. So we are still on chapter 3, diode circuits. This video relates to chapter 3C with two subtopics. The first one is filter circuit and the second one is voltage regulator. Okay, remember before this we have come across these building blocks. Okay, when these blocks are being used to convert AC signal to DC signal, and we already discussed this part where diode rectifier is being used, half wave rectifier, full wave rectifier, which is connected to step down transformer. So today in the first subtopic, which is on filter circuit, we are going to discuss this filter. Okay, for a filter circuit, as can be seen on this half-wave rectifier, there is an additional capacitor in parallel to a resistor, the load resistor. Okay, so we introduce filter simply by adding a capacitor in parallel to a resistor. At first, there is no charge across the capacitor. Okay, but as you know, when we talk about rectifier, right, we talk about Vs, which is the AC signal. Then in rectifier we consider positive half cycle and later the negative half cycle. Okay, so the same thing we are going to do now. So when we consider for the positive half cycle, okay, let's have a look for the first quarter of this positive cycle. Okay, at this time the voltage Vs starts from 0 until to the peak value, right? Okay, this portion starts from 0 until the peak. At this time, the diode is forward bias. Okay, because remember we can represent Vs like positive and negative like this. So we have forward bias connection, and obviously the diode will be on. Okay, so there will be a closed loop, and obviously there will be current flowing through the capacitor. So at that time we can say the capacitor is charging up. Okay, so we can somehow actually calculate the voltage when the capacitor is fully charged. Okay, where Vc is actually equal to V0, okay, because capacitor is parallel to the resistor here, okay, which is equals to Vs minus V gamma. Remember, we are talking about half wave rectifier. V0 equals to Vs minus V gamma. Okay, now we consider the next portion of the positive half cycle, because as Vs falls back towards 0, okay, because from the maximum value it goes down to 0 value, and even into the negative cycle, what will happen at that time? The diode will be reverse bias. Why? Because at this time, if you imagine the diode here, then here is connected to Vc, remember, when it is fully charged, and here it is connected to Vs, right? Okay, then this Vs, now because it's reducing, this Vs becomes less than the Vc voltage. That's why we are saying the diode now is reverse bias. Okay, so because the diode is reverse bias, open circuit here, no current flow, then obviously the capacitor will be discharging through the resistor. Okay, capacitor will be discharging. So that's why if you see from the graph here, okay, from the output waveform, you see there will be output voltage here, okay, but now it becomes reduced, okay, because now the voltage is being reduced because the capacitor is discharging over time. Okay, so that's why we're having this pattern here. Okay. Okay, then if you consider for the next positive cycle of the Vs, okay, so there is a point at which input voltage now will become larger than the capacitor voltage. Remember, I was showing you the diode where we have Vc and we have Vs, right? Okay, so remember before this Vc is decreasing because the capacitor is discharging. Okay, so there will be at a point at which Vs now becomes larger than Vc. At that time diode will turn on back. Okay, so the diode remains on until the input reach its peak value. Okay, then the same cycle happens. Okay, so as you can see from this output waveform, okay, the blue color line here is actually the Vs value. Okay, then let's have a look of the orange color line here. Okay, so for the first quarter, as we have discussed before, we are going to get V naught, which is equals to Vs minus V gamma. Okay, so that's why as you can see here, the orange color line here is reduced by how much? By V gamma. Okay, then later when we consider the next portion here, what will happen? Remember, at that time the diode is off, okay, and there will be no current. At that time the capacitor is discharging. Okay, so this capacitor is discharging because the diode is off. Okay, so there will be voltage, but this voltage will reduce over time. Okay, because the voltage across the capacitor is decreasing because the capacitor is discharging. But if we continue for the next cycle, there will be a stage where now Vs becomes larger than the Vc. Vs becomes larger than Vc. At that time, okay, we can get the diode on. Okay, we can get back the condition when the diode is on. At that time, the V naught equals Vs minus V gamma, this portion. Okay, then the same cycle continues, meaning to say if we were to consider for many cycle, it will be something like this. Okay, this is called the ripple voltage. Okay, then actually we can calculate the Vc value, which is given by Vm. Okay, what is Vm? The peak voltage of this output, exponential negative t, which is time, over Rc constants. Okay, R the resistor value and C is the capacitor value. From the output waveform here, actually there is one thing that you can have a look, pay attention on the ripple voltage, which is given as Vr. Vr is actually the difference between these 2 points, the maximum point and the minimum point of the ripple, and it is given as Vm minus Vm exponential negative t prime over Rc. But if we expand further this equation, actually we are coming to get the simplified form, which is eventually you are going to get in this form. Vr equals to Vm times Tp over Rc. Then for the half wave rectifier, the Vr actually can be calculated from this equation, Vm over FRC, where Vm is the maximum output voltage, F is the frequency, R and C obviously is the Rc constant. And for full wave rectifier, we can use this formula. It's just similar like half wave rectifier, it's just that we have additional 2 here. Okay, Vr equals Vm over 2 FRC. Okay, let's have a look on this particular example where we are considering full wave center tap rectifier. R is given, input voltage 120 volt, frequency 60 Hz. Then it mentions that output voltage cannot be lower than 100 volt, and V gamma is given. In this case, we are supposed to calculate for the C value, capacitance value. Okay, so as we know, since we are talking about full wave rectifier, we should use this formula. Okay, then for VM is actually remember center tap rectifier, Vm is actually equals to V naught, which is Vs minus V gamma, because we are considering second model, because only V gamma is being given. So Vs is the maximum output voltage, in this case is 120, okay, and minus 0.7, so that's why you are getting this answer. Then for the ripple voltage, the maximum one is 119.3 volt, but the minimum one, it is mentioned here, it shouldn't be lower than 100 volt, so this one is considered as the minimum value. So that's why we can get ripple voltage here, which is 19.3. So we have all the parameters, substitute in the equation, so we can solve for the capacitance value. Here is another example of filter circuit. We are considering full wave rectifier, but now we are considering bridge rectifier. Okay, so for this one, the capacitor is given, R is given, Vs value is given, V gamma given, then all you have to calculate is the ripple voltage. Okay, so in this case, we know we need to use this formula because we are considering full wave rectifier. Then frequency, we know it's 60 Hz, okay, from this 50 sine 2 pi 60t, okay, we know frequency is 60. Then from here we can calculate for Vm, but take note that now we are using bridge rectifier. Remember, for bridge rectifier, Vm is given by Vs minus 2 V gamma, remember? Okay, so that's why in this case 50 minus 1.4, okay, you are going to get the output voltage, the maximum output voltage. Then from there, you substitute everything, then you can get the ripple voltage, in this case is 2 volt. For the second subtopic, it's on voltage regulator. So as can be seen from the building block, we started out with the diode rectifier, where we convert the AC signal to one polarity. Then this one polarity signal is being connected to a filter. Then later we can get the ripple voltage. Then this ripple voltage will be connected to the voltage regulator, which we are going to discuss later, because at the end of the day, we want to produce a straight line to represent the DC voltage. So basically, for voltage regulator, as the name it is, it will supply constant voltage to a load. Okay, so in this case, voltage regulator is made of Zener diode, and it is being connected in parallel to a load, which we are going to see in details later. Okay, for this voltage regulator circuit, we make use of the breakdown voltage across the Zener diode. So whenever the Zener diode is on, the voltage across the diode will always be equal to the Zener voltage. So as can be seen in this voltage regulator circuit, the Zener diode is connected in parallel to a load resistor. So as we know, the Zener diode will always hold the voltage constant regardless of the current. So although VPS value might be changing and current also might be changing, but as long as we have this Zener diode connected here, the voltage across the diode always will be equal to the Zener voltage, and as a result, the voltage that will be across the load resistor also will be the same constant voltage similar to the Zener voltage. Okay, there are a few things that we need to consider related to voltage regulator. The first one is, since we are making use of Zener diode, so we need to consider the minimum current IZ min as well as the maximum current IZ max in Zener diode. And another thing is, we should take note, V load should be always equal to Vz, because remember, they are connected in parallel. So whenever we are having Zener diode with a constant voltage of Vz, always the same voltage will be observed at the load resistor. And another thing is, we can consider KCL equation for the current. II equals IZ plus IL, because if you see from the circuit, II is split into two, which is IZ on this path and IL on this path. And another thing is, VRI equals VPS minus VZ, because we can do actually KVL equation for this closed loop. Let's have a look for this example for you to better understand about the voltage regulator circuit. Okay, as can be seen from here, a Zener diode is connected in a voltage regulator circuit. Okay, then VPS is given as 20 volt, VZ is given as 10 volt, Ri is 222 ohm, and PZ max is given as 400 milliwatt. Okay, then you have to determine the values of IL, IZ, and II if RL is 380 ohm. Okay, so first thing what you have to do and to take note is VZ is given as 10, Zener voltage is given as 10. So automatically you know, since the voltage here is 10, obviously the voltage across this RL also equals to 10 volt. Then obviously from here you can simply calculate for IL, which is given by V across RL divided by the resistor value, which is 10 volt, remember, because it's parallel to the Zener diode, and divided by RL, which is 380 ohm. So in this case you are getting the IL value. Okay, then the question is asking us to determine the values of IZ and II as well. Okay, so in this case what we can do is, remember here we have one closed loop where we can do KVL, right? So in this case, let's have a look. Negative VPS plus II Ri plus VZ equals 0. Okay, so in this case you can calculate for II, which is VPS minus VZ divided by Ri. Okay, VPS given as 20, VZ 10, Ri is given as 222 ohm. So obviously we can calculate for II. Then remember, we have this KVL equation where we are saying II is actually equals to IZ plus IL, right? So from here we already know IL, we already know II, so obviously we can simply find for IZ. Okay, so we are done here for the first part, and later we need to determine the value of RL that will establish PZ max equals to 400 milliwatt. Okay, meaning to say the maximum power dissipation, okay, for this particular circuit is 400 milliwatt. Okay, so as we know, PZ max, okay, is the power equals to VI, right? V obviously is the Zener voltage, and I obviously is the IZ, but in this case it should be the IZ max, maximum current that flowing across the Zener diode. So in this case it's given as 400 milliwatt. Then VZ always constant as 10 volt. From here you can calculate for IZ max. Okay, so now we know the IZ max value. Okay, then the II value is not changing because VPS, VZ, Ri is, they are just still the same. So we are having the same II value. Now we can have a new IL value, right? Because now we are having IZ max. Then II is just the same value. Now we are having a new IL value. Right, so in this case we can calculate for this new IL value. Then obviously from here IL new, okay, will give us the RL new value, okay, because V equals to IR. So the answers are given there. Okay, you can double check afterwards, okay, whether whatever we discuss giving us the same answers. Okay, another thing that you should take note that sometimes this voltage regulator may comes in a range of power supply, meaning to say this VPS is not constant, it may varies in a certain range. Okay, so to properly function this voltage regulator circuit, there are few conditions that we have to follow. First one is power dissipation in the Zener diode is less than the rated value. Meaning to say, remember for previous example, we are saying the power dissipated across the Zener diode is 400 milliwatt, right? Okay, so if we if we were to use any Zener diode, we should check the data sheet where the maximum power dissipation allowed to happen across this Zener diode should be larger than 400 milliwatt. Okay, if that is the case, then only the diode won't get damaged during the operation, meaning to say the rated power dissipation value should be larger than the calculated or the measured value. Then you should take note as well. Remember, we are talking about VPS having a range. It could be having maximum value, minimum value. So when VPS is minimum, okay, at that time IZ will be minimum. Okay, when VPS minimum, IZ will be minimum. Then obviously, since less current will be flowing here, IL will be maximum. Okay. In other condition, when VPS becomes maximum, at that time IZ is maximum, then obviously since more current flowing through the Zener diode, IL will be minimum. Less current will be flowing through the RL. You should understand these two concepts. Okay. Then how do we do the analysis for this particular voltage regulator with a range of power supply? Remember, actually from this we can get the KVL equation, okay, where from there we can actually get the RI value. Okay, so if I were to show you minus VPS plus IIRI plus VZ equals 0, right? So in this case, our RI is VPS minus VZ. Then this II is actually IZ plus IL. Remember the KCL value? Okay, KCL equation. So from this RI equation, we consider the condition when the VPS becomes minimum. Okay, so as you can see here, when VPS minimum, IZ will be minimum, then accordingly IL will be maximum. Then for the same RI value, when we are considering VPS maximum, IZ should be maximum and accordingly IL should be minimum. Then if we were to equate these two equations together, we are going to get this long equation. But I won't advise you to do so. I will show you in example later. Okay, then another thing that you should take note is we can actually approximately equate IZ mean with the IZ max, where IZ mean is actually equals to 0.1 IZ max. Okay, so we can substitute whatever IZ mean value with 0.1 IZ max. Okay, then substitute into the equation. Eventually you are going to get something like this. Okay, but again, as I mentioned just now, you don't have to memorize this. Okay, I will show you how to get this IZ max later. But at the end of the day, we can actually calculate for the maximum power dissipation across this Zener diode, which is given by this formula. Okay, let's have a look for this example. This is condition where the power supply is varied, okay, in a certain range. Okay, so as we can see here, we consider a voltage regulator circuit which is used to power a cell phone at 2.5 volt from the lithium ion battery, which voltage may vary between 3 and 3.6 volt. Okay, so this is the condition where VPS maximum and VPS minimum, and the current in the phone will vary from 0 when it is off to 100 milliampere when the user is talking. So you have to calculate the value of RI and the Zener diode power dissipation. But first we have to identify what are the parameters here. Okay, so in this case, as we know from this example, the voltage may vary between 3 and 3.6 is actually the value of VPS, where VPS min is 3 volt and obviously VPS max is, in this case, 3.6 volt, right? And it mentioned that the cell phone, the power, the voltage regulator is used to power the cell phone at 2.5 volt. Okay, so actually this is the VZ value 2.5 volt, and the current in the phone vary from 0 to 100 milliampere is actually at the load. Okay, so IL is minimum at 0 and IL maximum is at 100 milliampere. So in this case, remember we consider the RI value where equal VPS minus VZ over IZ plus IL, right? Okay, so let's consider for the first case where VPS minimum. So VPS minimum is 3 minus VZ, which is always 2.5, divided by when VPS minimum, IZ also minimum, right? Okay, then obviously at that time you are having IL maximum. Okay, so IL maximum is 100 milliampere, right? Then for the same RI equation, let's consider when VPS maximum. When VPS maximum is 3.6 minus VZ, still 2.5, divided by IZ max plus IL mean, which is equal to 0. Okay, so in this equation you are getting IZ mean and IZ max, two unknowns, right? But as you know, IZ mean is actually 0.1 IZ max, remember? So you can actually substitute this IZ mean with 0.1 IZ max. Okay, then rearrange this equation, you are supposed to get IZ max value simply from this. Okay, meaning to say you don't have to consider all this long equation. Okay, you just start from scratch to calculate for IZ max. So now, since if you consider the approach that we discussed just now, eventually you are going to get IZ max value is at this 282.05 milliampere. So this, in this case, we are supposed to calculate for RI, remember? So this IZ max you can actually substitute into here, then obviously you can get the RI value, how much. Okay, so as can be seen from here, this is the RI value that we are supposed to get. Then remember, the question is also asking for maximum power dissipation. So simply we can substitute into the formula to get the maximum power dissipation in this particular circuit is 705.13 milliwatt. Meaning to say, whenever we choose the Zener diode for this particular application, okay, for voltage regulator circuit, we should choose a Zener diode with a power rating larger than 705.13 milliwatt to make sure the diode is not getting damaged throughout the operation. Okay, this particular example, I leave it to you to do your own self-revision because all the values are being given. It's just similar to previous example. It's just that for this particular example, as you can see here, RL is given in the range of 20 to 100 ohm. Meaning to say, RL minimum is 20 ohm and RL max is 100 ohm. Okay, so in this case, since RL min is 20 ohm, so you can actually calculate for IL, which is VL, where VL is actually the VZ value because they are in parallel, right, over the RL. Okay, so if you are using RL minimum, obviously you are going to get IL maximum. Okay, because less resistor will be more current. Then the same thing if you are using RL maximum. Okay, so obviously this IL should be the minimum value. Okay, then later you can substitute accordingly to find for the IZ max. Then later from there you can find for RI, then obviously the maximum power rating of the diode. So later we are going to discuss this particular example. So let's recall, we are supposed to know about two subtopics. The first one is on the filter circuit and the second one on the voltage regulator circuit. So that's all for video 3C. Thanks for watching. Bye.